relatively recently, but I felt intellectually extremely stimulated by his sort of breadth and how he sees interconnections between everything. I think more than that, but with the joy with which he does everything. I think there's one word that we heard in our discussions again and again. Oh, that's great fun. I really deeply admire that. And in the same spirit, as you say, we're going to talk. The last talk is Big Bang and Culture Bang. Okay. So this really is, in some sense, a continuation of John Baez's talks, but more properly, the first three talks that he gave. I'm not going to use at all in this talk the nice results on spin foam that John described and that are emerging basically every month. So if you look at from a physics perspective, and one wants to know what are some of the big questions of quantum gravity, big physics questions of quantum gravity. Well, the first question, I'll go through this list quickly, and we're going to see some of them in some detail later on. One is that classical general relativity predicts that the universe began with the Big Bang, or there was this initial singularity, and everybody believes that any time a physical theory predicts infinities, it means that we are applying it in a domain which is beyond its proper region of validity. And so, if so, something else will replace general relativity, and then in that theory, what would replace Big Bang? As I will explain, with black holes, there has been a question which has been around for about 25 years now, which was perhaps the most celebrated result of Stephen Hawking, which implies that at least large macroscopic black holes should have an entropy which is proportional to that area. And the question is, well, does quantum gravity actually explain this? Then the other question is really, are the ultraviolet divergences cured? As Dennis pointed out in John's talk, in a certain sense, since there is fundamental discreteness, we don't have continuum space-time, maybe the ultraviolet divergences of quantum field theory would not be present here, and certainly in this spin foam model, one sees that. Then a very important question is really about the semi-classical sector, and this came up in a discussion, I think, yesterday. The way that this theory is constructed is really in a background independent and non-perturbative way. So we do not begin with the space-time and add gravitons or some perturbative things and hope to build quantum gravity for that. The whole spirit of the approach is that geometry, like all the matter fields, are sort of say born quantum mechanically. But this is very nice, but on the other hand, this theory lives in this abstract world, which is rather pristine and abstract. It's all very nice, but how do you make contact with the everyday phenomena that we see around us? It is true, as John pointed out, that the basic emphasis is to start with general relativity, or perhaps supergravity, and then pass on to quantum theory by taking these equations over. So one is, in some sense, really quantizing a classical theory. So from that perspective, it is clear that in the standard way that one does physics, that general relativity would emerge as a classical limit. But the question about semi-classical sector is really the following. That finally, one is going to solve this Hamiltonian constraint, say, a la Thema, and then one is going to get all these states, which one wants to call physical states. And the question is, among these states, which satisfy the constraints as precisely formulated, which satisfy the Einstein's equations as formulated rigorously, are there states which represent classical spacetimes and fluctuations perhaps around those spacetimes? Or do we have an exotic sector? If I look at 2 + 1 dimensional quantum gravity, then indeed there are sectors of the theory, one can quantize similarly, but when you have the quantum theory, there are sectors of the theory which are semi-classical limits, and there are sectors of the theory which do not. So which sector are we living in? So that's the kind of question that one wants to ask. And finally, are there observable consequences of fundamental discreteness? And there are really some ideas that people are pursuing about this.
The second last question, is that analogous, is what you just said analogous to like the other discussion, I think a Boltzmann discussion, and then you take a thermodynamic limit, you get a smooth picture. Is there an idea of a thermodynamic limit of the quantum theory that reaches the classical?
Right, so I think this large volume limit is often called the thermodynamic, the infrared limit is often called the thermodynamic limit. But the more...
That's not how you try to find this classical...
No, that's not how one tries to find.
Should, because it's quantum method appearing at a small scale.
Right, so one is doing coarse grading.
But, idea, right?
Yeah, so one is doing coarse grading in order to get the continuum limit. But it's not, one is doing coarse grading, so one is looking at observables, not at the microscopic scale of, but it's on coarse grading. And then how does it think about that? But in this talk, I'm just going to talk about the first two issues, which have to do with the Big Bang and black holes. And I just chose them just because, it is 1 hour and I can only do so much. But they also illustrate that the essential features of the quantum geometry framework that John described play a key role in all these things. So there really are two somewhat disjoint parts to my talk. The first one is a smaller part. I chose to make this shorter because in some sense this is not mathematically rich. It is conceptually very interesting. And that is just what happens to the Big Bang singularity. And this is all based on some papers by Martin Boyewald, which are rather recent. The first one has already appeared in Physical Review Letters. The second one will soon appear. And these are the references. And for the Los Alamos archives. And the second and the longer part, I will talk about quantum geometry of horizons and black hole entropy. The classical part of this work was done with Alexander Korici and Kirill Krasnov and myself. And the quantum part was done with John and Kirill and me. Okay. And here are some references for that. Okay, so let me begin with the first part, and let me just sort of say in a little more detail what the issues are. So we're looking at this Big Bang. So how does Big Bang arise in all this thing? So we can look at classical general relativity to begin with. So here I'm just constructing the setting, so to say. And the question is, we want to look at the large-scale structure of the universe. We don't want to know about solar systems and stars and so on, but averaged out large-scale structure. And one finds that to a very good approximation, on a large scale, the universe has some symmetries. The universe is spatially homogeneous. It really doesn't matter where you are, so to say, on a sufficiently large scale. And it is isotropic. There is no preferred direction in space that is chosen. Mathematically, this just says that the 4-manifold M is foliated by 3-dimensional submanifolds, which represent space, and the remaining direction is time. And these submanifolds are 3-dimensional manifolds of constant curvature. And therefore, the 4-dimensional metric, if you like, just looks like a minus dt squared up here for the time. Then a scale factor, function only of time, doesn't depend on space, times a spatial metric. And the spatial metric could be a 3-sphere metric, so unit 3-sphere metric, or the flat metric on R3, or the unit hyperboloid metric. You can easily calculate curvature of these without just geometry. And you, of course, find, just by dimensional reasons almost, that the curvature goes like 1 upon the scale factor squared. Now we got Einstein's equation, which says that certain tensor, it's called Einstein tensor, which is constructed out of the curvature of this 4 metric, is equal to 8 pi times Newton's constant times the stress energy tensor of whatever matter you have. But because we got all these symmetries, that means nothing depends on space coordinates. Everything just depends on time. And then therefore there is a huge simplification. Einstein's equation reduced to ordinary differential equations. And if you assume that the matter that you have satisfies some physical energy conditions, that is physically appropriate matter, then the conclusion is you can solve all these equations, just total differential equations, and the statement is that there really is a Big Bang. That is to say, in each of these solutions, the universe, you can find a point at which the universe shrinks to 0. So A goes to 0, so the volume of the universe goes to 0, and well, for simplicity, I'm looking at the S3 topology. Then the volume of the universe goes to 0, and the curvature, which goes like 1 upon A squared, goes to infinity. So as I just mentioned early in the introduction, the prediction of a singularity by a theory just means that the theory is pushed beyond the domain of its applicability. And so the big question is, do quantum effects intervene, and what replaces space-time? And sort of a huge, a heuristic intuitive idea is something like the following. If you take magnets, ordinary magnets, one understands the theory of magnets, and usually, of course, there is a vector called magnetization, the thing which points from south to north, that we always use. that is the ferromagnetic state, and you can measure it, and you can measure how this changes in the external magnetic field, that is called the susceptibility, and so on. But if I heat this magnet, then a stage comes in which this description in terms of in terms of magnetization and susceptibility is not a very good description. There's a phase transition, and you go to a phase called paramagnetic phase. So what happens is that at that phase transition, the magnetization goes to zero, a little like that, and the susceptibility goes to infinity. So, well, of course, there's nothing wrong with this magnet. It's perfectly fine. We just cannot use this particular theoretical description with the magnetization and so on. We have to replace it by microscopic description. We have to look at the magnet quantum mechanically. And if you look at it quantum mechanically, it is described in terms of spins, and then you are going to Hilbert space of states, and you can compute things. It's just that this approximation of a magnetization is like a classical or a mean field approximation that fails. And the idea is that perhaps similar thing happens at the singularity, that the metric and the curvature that we compute are like in some sense mean fields, and they blow up. But on the other hand, there is nothing wrong. And if you look at the physics in terms of microscopic building blocks, like for example the spin networks, then maybe everything will be okay. And the other question really often is raised is, well, are there initial conditions? What are the initial conditions for the universe to start? If in fact everything is regular, what are the initial conditions? Now, these questions were addressed in a branch of quantum gravity called quantum cosmology for many years now, more than 20 years, actually more than close to 30 years now. And the idea here was always that what you do is you go to look at general relativity, and you first symmetry reduce the theory. So you first impose all these conditions, and then you reduce the problem. The only variable is just the simple A of t, the scale factor, that is the only variable that is left over. So you reduce general relativity to ordinary quantum mechanical problem, and then you try to quantize. So first, classical theory symmetry reduce, and then you try to quantize. Then the idea is that you would get some quantum state of the universe will be represented in this simplified model by a wave function or a state in a Hilbert space, which depends on the scale factor and on whatever matter fields you have. Unfortunately, in all these attempts, it turns out that the singularities persist unless some new elements are introduced by hand. And the new elements could be you introduce some exotic matter which doesn't satisfy physically reasonable boundary energy conditions, and therefore you get a bounce of some kind. So you have to contrive things in order to avoid this singularity. And all this was really done, this quantum cosmology, standard cosmology, was done using the metric variables of John Baez's first talk. Now the new strategy that Martin Boyer-Wald came up with is the following: that he wants to retain the essential features of quantum geometry. We don't want to first symmetry reduce the system, reduce it to ordinary quantum mechanics, and then the scale factor is just a continuum, right, a continuous function. The volume is just a cube, so it's just a continuous function, and so on. So the idea here was that why don't we first quantize, for example, the way that John explained to us. Then we'll get a Hilbert space of states, and on that Hilbert space, you will get all the geometric operators, which are discrete spectrum, like the volume, the scale factor in this case, and so on. And then we should take that seriously, and then impose the symmetric condition, and then see what happens. So it is really, at the kinematical level, one is first beginning with a full theory, then imposing the symmetry conditions. So what John talked about was really the following.
Well, kinematically, I mean like the background.
Say it again.
Kinematical, by that you mean like the background?
No, kinematical meaning the spin networks and without imposing Einstein's equations.
It's the basis.
The basis, exactly. The basic framework without introducing Einstein's equation to begin with. And as John told us, that we got this space of functions which is spanned by the spin network functions. If you take finite linear combinations of this spin network, we get a certain space which is called the space of cylindrical functions. And this is contained, a Cauchy completion of this gives us a certain Hilbert space and the space of generalized connections with respect to this uniform measure. And John really sort of talked about these two spaces. But in fact, there is also sort of a Gelfand triplet. You can also look at functions, which are linear functions on the cylindrical function setup here. And you can think of them as being distributions on the space of connections. So these are all nice functions. These are the Cauchy completion, and these are distributions on the space of generalized connections up here. And in fact, when you solve the quantum constraints, as John told us, in the general theory, not just in this theory, in this model, then those solutions to quantum constraint always belong to this more general space. And the semi-classical states, which would approximate, for example, Minkowski space with gravitons or photons, also belong to this particular space here. And now, the idea is that we look at the homogeneous isotropic cosmology, and then we are going to look at states in this space which are distributional. You see, the states in here can be distributional, so they can have support only on those connections which satisfy our symmetry conditions, namely which are invariant under the action of this group, which is homogeneity group and isotropic group. So to say, what we have is basically the isometry group of the three-dimensional space, and we're looking at wave functions which are support only on those connections which are symmetric with respect to this isometry group. It's a little like looking at all possible connections and focusing your attention on the space of flat connections, which of course is a very small subspace, the space of all connections, and functions which are support on this will be sort of distributional. It's very similar to that. But then what one does is to use the operators, quantum geometry operators, like the volume operator. One doesn't introduce them ad hoc here. We already have volume operators, area operators, etc. sitting on this space. So we can say, well, what do they do to this particular symmetric states? So they descend from the full quantum theory that John described for us. And in particular, the scale factor operator, A hat, has all discrete eigenvalues. But the continuum limit, by the way, is reached very rapidly. For example, there's an eigenvalue close to a centimeter, and the next eigenvalue is 1 plus 10 to the minus 66 centimeter. So the spacing is so small, so short, that there's an approximate continuum description, but nonetheless, at a fundamental level, there's a discreteness. Now, the problem usually was the following, that in the classical theory, well, the curvature is always goes like 1 upon a squared, and when a goes to 0, the curvature blows up, and that is our singularity. But now, in this particular way of doing quantum mechanics, we want to quantize the curvature operators. But the quantization of curvature operators is the same as a quantization of curvature functions to operators is the same as quantization of the function 1 upon a. But now a actually has 0 as a discrete eigenvalue with some degeneracy, and therefore we cannot quite take just a hat to the minus 1. It's not a self-adjoint, density defined self-adjoint operator of the Hilbert space. So we have to take the curvature functions like 1 upon a fresh, and we want to find out operators corresponding to that. And what was nice was that again, one did not just invent some regularization, some factor ordering, etc., but rather one looked at corresponding functions in the full theory that John described, and there is a procedure that Thomas Tiemann had introduced to regularize operators like the 3 metric divided by the square root of the determinant of the 3 metric. It's a horrible looking function, but there is a nice procedure to quantize such an operator, and that is what was applied to get an operator corresponding to 1 upon a. And the operator on the Hilbert space corresponding to 1 upon a, is 1 upon a hat, has all the pleasing properties, namely, first of all, it commutes with 1a, as it must. They have the same eigenvectors. A was a scale factor. A was a scale factor where all the dynamics is coded, all the physical information is always coded in this radius of the sphere, if you like, radius of the universe. Therefore, you can think of it as a volume of the universe, if you like, roughly. And the volume is quantized, as John told us, and therefore this quantized. But then, the very surprising thing is that, in fact, the operator corresponding to 1 upon a is actually bounded above, even though the operator corresponding to a has a discrete 0 eigenvalue. And the bound is such that, as h bar goes to 0, this bound goes to infinity, corresponding to the classical prediction or classical consideration that as a goes to 0, 1 upon a should go to infinity. And by the way, this is a physics remark. This is exactly what happens to the hydrogen atom spectrum. The ground state of the hydrogen atom, classically the ground state and energy is infinity, but quantum mechanically it is normalized because of Planck's constant. It is brought up and made finite because of Planck's constant. And now finally one might say, well, it is very strange. You have got the operator corresponding to 1 upon a, you have got the operator corresponding to a, and you're saying that this operator has 0 as an eigenvalue, but this operator is bounded from above, maybe you used a very strange quantization. But in fact, in other words, it really is this operator close to the inverse of this operator, at least in some regime? And the answer is yes. In fact, if you just look at the eigenvalues of these two operators and see how they go, then the product of the eigenvalues should be 1, you would expect. And already at roughly speaking at 6 Planck lengths, 7 Planck lengths, and Planck length is 10 to the minus 35 meters, the product becomes 1 and it remains 1 all the time. But for smaller Planck, for smaller values, smaller eigenvalues, where quantum gravity effect should be most important, like the near the Big Bang, where A is equal to 0, there's a big difference. The product of these two eigenvalues, A times B, eigenvalues of A and 1 upon A hat, actually doesn't go to 0 at all, and doesn't go to 1 at all. There's a major difference. So the statement is that whatever surprise we have from this operator, it really is deep in the Planck regime, and so we should not worry that this is an operator which is an ad hoc factor ordering, etc., etc. But in any case, the factor ordering descended from the full theory, and so it is not ad hoc, but one can still make all the checks. And then finally, the second surprise is the following. You can use quantum Einstein's equation, and here we are using this difficult equation that John talked about, which is called the Hamiltonian Constraint equation. We can take this quantum mechanically and say that, well, supposing you take a general state of quantum theory, which depends on the geometry through A, and which depends on some matter fields phi, for example, and we can just expand it out in the eigenbasis of the A operator or the volume operator. A is like the volume of the universe. So you can just do that, then you get an expansion like that, and the quantum Einstein's equation, the Hamiltonian constraint, again, one is not inventing any new things, one is taking the Riemann's regularization, the full theory, and applying it to this case. Not very surprisingly, perhaps, it becomes a difference equation rather than a differential equation, where Cn, Dn, and En are just numerical factors. So we just evolve. You give me the wave function at n minus 4, and n, then I tell you what the wave function is at n plus 4. So time steps, if you like, are discrete, and we can just evolve to these discrete steps. These time steps are very small, so for large volumes of the universe, large number of the Planck length, it approximates a continuous differential equation very, very well, but at small scales, it is quite different. And the statement is that the important key point is that there is no problem at all in evolving this equation through A equal to 0, or if you like, through n equal to 0. Furthermore, there is a very nice thing about initial conditions. This has been a subject of great debate and various thoughts. For example, people like Hawking, others have proposed boundary conditions that they like for the beginning of the universe. And other people have felt, well, but this is put by hand, etc., etc. Here something very interesting happens. If you require that your solution for large volumes, when the universe is very large, your solution should not jump around too much, right? I mean, as it is evolving from one Planck step to next Planck step, it should not jump around too much. It should be approximately semi-classical for large volumes. And this is called the Preclassic Galaxy condition. That automatically selects a unique solution. This is difference equation has very interesting properties, and they just come out. Nothing is put by hand. And what one finds is that for large volume, the universe becomes very classical, and near the Planck volume, very, very close to the Planck length, when the universe is very, very small, close to the Planck length, there are major departures, but one can evolve through what are the classical singularity and see what is on the other side. In this magnetism analogy, it's like the other phase in some sense. It's a very rough analogy. And on the other side, the statement is that there are large quantum fluctuations, and so space-time dissolves. We cannot have a classical description at all. There are Planck's, big quantum fluctuations, so we cannot define a classical metric. But the spin network functions, the states that were defined in the Hilbert space are perfectly fine, and we can do our evolution without any problem. So there is agreement with the standard metric-based quantum cosmology for large times, but for example, times less than about 10 Planck times, Planck time is 10 to the minus 43 seconds, it's very, very small, there are major departures up here. So this seems to do what one heuristically, intuitively hoped it would do. We don't put in elements which are ad hoc. We start with what we had in the full theory and see what happens in the case of cosmology. And one finds that classically there was a singularity, quantum mechanically there is no singularity, but for large volumes the predictions are very similar to the classical theory, and the notion of space-time dissolves in a very specific way, and the key element that is used all along here is really the quantum nature of geometry. The fact that the volume operator has discrete spectrum, that you have got this difference equation. Okay, so that is the first part and the smaller part. The second part I want to talk about is about black holes. So let me just explain the main issues up here about black holes.
So like there's no way to test the predictions. You test it with philosophical.
I think
theory.
there are some issues. I mean, that people. This is rather recent, so people are not working on everything, but there could be, because one can say now, okay, this is semi-classical at 10 Planck times, but it's not completely semi-classical. So what are the signatures that are left over there for quantum gravity signatures, and what do they do for the evolution of the universe? And people are quite interested in this. The observation people are very interested in this. I don't have any idea about how much work can be done, but that's the direction of work now. No, it's completely, second part, which has to do with black holes. So black holes are these exotic objects that we all know that there are predictions of general relativity, that they exist.
Well, what are they?
Okay, black holes are perhaps the best. In the most pristine form, black hole is pure geometry. And what we have is, we have got a Lorentzian space-time, and basically there is a region in the Lorentzian space-time where the light cones, at each point in the space-time there is a light cone, and that tells in space and time, and that tells us where which event in space-time can be causally connected to the event that you start out with. In the black hole region, so we can say that here is a picture of space-time. Think of this as being time, this as being space. And if you are out at infinity, then the light cones look like those in Minkowski space. They are all very nice. But there is some curvature region up here, and because of gravitational attraction, the light cones start tipping, and there can be some surface up here, which for example is formed by stellar collapse, in which light cones are tipped so much that all the light rays are inward. There is no light ray which will actually go out. And therefore this region of space-time is completely invisible from the exterior, and this boundary of the region, which can come, a signal from here can go out, light cone up here is bent like that, but I can still send out a signal just like that, and that will go out to infinity. So this is the exterior region, this is the interior region, this is called the black hole, and the boundary is a certain null surface, and null three-dimensional surface, and this is called the horizon. Yeah, it's a geometry.
How the cones are pointing.
Right. How the cones are pointing is really, this is the future light cone, so these are the time-like directions and null directions going that way. And so this is just the geometrical picture of space-time diagrams. What we would be interested in is in the canonical picture, so taking a slice like that. So three-dimensional manifold, this is the four-dimensional manifold. And then the intersection of the horizon with this three-dimensional slice is a two-sphere. And we'll be often interested just in these two spheres. Okay. So there are, in general relativity, these objects exist. Yeah?
Grow like that?
Say it again.
Does it grow like that?
The area in general can grow, if things are following. This is, so the set, this is a null surface, so I try to show that it's going. If nothing is falling into the black hole, then the area is constant. And then if nothing is falling, the area is always constant, if you like. So this is the surface area that is completely constant. This is the region we'll be interested in. But if something falls from the black hole, then it grows.
I was worried that I'll get up there.
Say it again.
I was worried that I'll get up in one.
Yeah, you may actually. Right, exactly. There may be a, yeah. Okay. Now, laws governing, so general relativity has some laws governing black holes in equilibrium. And what they say is that these laws, they tell us some, how, if you have a black hole which is sitting there in equilibrium and you go and tinker it, you just drop something in it, etc. How does it react? What happens to the black hole? And these laws look very similar to the laws of thermodynamics. If you think of the area of the black hole as being proportional to the entropy of the black hole. Somehow if you assign an entropy to the black hole, why you should assign, it's not clear at all a priori, but there is a mathematical similarity if you say that the entropy is proportional to the area. Now Hawking did his famous calculation in 1974. What he did was to look at quantum field theory on a black hole space-time. So somehow you are given a space-time with a black hole. Gravity is classical, space-time is classical, and matter fields are quantum mechanical. And he did a detailed calculation to see what happens if you send out a vacuum state, what you get out at infinity, etc. And his results gave us the proportionality factor, and they told us that the entropy, in fact, is given by 1/4 of the area of the black hole horizon in the Planck units. G times h bar is just Planck length squared. And therefore, a challenge to quantum gravity had been to account for this expression from first principles, that is to say, account from it from statistical mechanics. In other words, we would like to think of this black hole as having some ingredients, which are, like the entropy of the gas in this room. We will start with looking at the gas as a bunch of molecules. We will construct an ensemble, and we will calculate the number of states in that ensemble subject to some condition like the volume is fixed, the pressure is fixed, and they take the logarithm of that, and that gives us entropy. So what should we similarly do for a black hole? That was the question. Well, first of all, there are many thought experiments that were sort of analyzed, and they all support the idea that in fact the entropy of the black hole should be 1/4 of the area, and that actually is required for consistency between general relativity and thermodynamics. And the interesting thing is that in this whole analysis, to begin with, classical general relativity did not know anything about h bar. Hawking's calculation knew about h bar because he brought in quantum field theory in curved space-times. And the interesting thing is that harmony between thermodynamics and general relativity is restored if you have h bar. If you do not have h bar, there is no quantity you can construct which is sort of dimensionless. Entropy is a logarithm of number of states, so it's dimensionless in these units, and therefore you need a Planck length. Therefore you need an h bar. So all these things came together, and that is why one believes that this is a very fundamental result, and somehow you should, even though Hawking obtained it approximately, we should really be able to get it exactly. So now there are all these heuristic ideas as to how to get this black hole entropy, and perhaps the most the one which fits together with quantum geometry very nicely was suggested by John Wheeler. See, if you take black hole entropy and you want to calculate black hole entropy, supposing you have a black hole of 1 solar mass, supposing if in fact our sun were to collapse and form a black hole, then how much entropy should this sun have, that black hole have? Which is given by area upon Planck length squared. You can plug in the area of the horizon, that would result. And this is absolutely huge, it is 10 to the 77. So the number of states is huge, it's exponential of 10 to the 77. And at least for physicists, this is a very large number. And so the question is, how are we going to account for this large number? Where is it going to come from? And the idea that Wheeler suggested was that what we should do is the following. See, classically, we can look at this surface, the horizon of the black hole, these two surfaces that I was drawing up here. And classically, it looks like a nice two sphere. The geometry is all smooth and so on. But if you zeroed in microscopically, maybe the geometry is not smooth at all, but in fact it may be natural to divide this horizon into sort of cells, elementary cells of area Planck length squared. Why? He doesn't know. I mean, he's just saying that maybe we should do this. And then maybe each cell really has a bit of information, that is to say 2 states. Maybe there are 2 quantum states associated with each of these cells. If that is the case, if the total number of states goes as 2 to the number of, total number of states goes as 2 to the number of cells. Number of cells is the total area upon Planck length squared. And therefore, if I take the log of this, the log of the entropy will be proportional to n, and n is just proportional to area apart from units up here. And therefore, this is how you would obtain the entropy to be proportional to the area. But of course, this was just a heuristic idea, and I think people thought it was cute, but nobody took it too seriously because one didn't really know in those days how to why one should divide the horizon area into all these cells. But as John explained to us, the area operator is actually quantized. In other words, eigenvalues of the area operator are not continuous but are discrete. And then now suddenly, from the perspective of quantum geometry, it becomes very reasonable to consider such a picture. But quantum geometry, of course, was constructed generally without any black holes in mind, as John explained to us. And then it was applied to this black hole problem. And what we find is the following. You take general relativity plus the condition which says that there is a black hole, that is to say the horizon, there is a black hole horizon. Plus you take the background independent quantization that John described. That tells us, this is what the purpose of the second part of the talk is, that tells us that the horizon geometry can be described by the quantum U1 Chern-Simons theory. So this is not SU2 Chern-Simons theory, but it's a very much simpler U1 Chern-Simons theory, just abelian Chern-Simons theory. On a punctured 2 sphere. And how does this puncture arise, etc., we'll see. And therefore there's a detailed theory now of quantum horizons, and you can count the states, and the states, the number turns out to be, the entropy turns out to be proportional to area, and therefore Wheeler's picture of it by bit, the bit was supposed to be these 2 states, and it is the entropy. So the entropy via these 2 states is actually realized. Now to go in some details, this is for the mathematical part of the audience, so to say. So I'd like to explain the setting and why you get Chern-Simons theory. So that is my second thing about black holes. Why Chern-Simons theory? Well, what you can do is there's a whole classical theory that was developed in order to tackle this problem, which is called the theory of isolated horizons. That is to say, we are looking at black hole horizons, which are isolated. Nothing falls into that. And the laws of black hole mechanics were generalized in this isolated horizon case. And so what we want to do is to consider sort of either in the space-time picture, Lagrangian formulation, or a Hamiltonian formulation. And what we want to do is to consider here the Hamiltonian formulation. You've got a 3-dimensional space manifold, and there is an inner boundary to sphere, and this is a black hole. So what is accessible to the outside observers is just this region. They cannot see what is going on in these 2 spheres. And now there are geometrical fields on this manifold M. And these are the fields that we heard about, namely, we've got a connection A, which is an SU2 valued spin connection, and there are what John called the triad E, but I think for mathematicians, I think it's much easier just to take its dual, and the dual is just a 2 form. So this is just a 2 form which takes values in the Lie algebra of SU2. So we got, these are the dynamical variables on this surface up here, and it is this that John looked at quantization of and got to spin networks and quantum geometry. But now, if we look at this black hole boundary condition, what that tells us is the following. It says that if I take this connection, and if I put it back to the horizon, then in fact it's a reducible connection. That means it is completely determined by a U1 connection just living on the 2 surface up here, which we will call W. So this is not obvious. This is just something that happens when you look at detail, the boundary conditions which say that this surface is not any old surface, but this surface is a black hole horizon. And the boundary condition says furthermore that whereas in the bulk, in the volume, A and sigma are completely independent, on the boundary they get related. Namely, I can take the curvature of this U1 connection I can take the curvature of this U1 connection, I just call it F, that is proportional to this 2 form, these are 2 forms, that is proportional to the pullback of this 2 form, the triad 2 form, on the surface. So W is coming from here, and this is coming from here, and where the internal direction is contracted with the internal radial vector. So this is a radial vector, the Lie algebra of SU2. With a precise numerical factor, that is minus 2 pi upon the area of the horizon, times this Barbero-Emirzi parameter gamma that John told us about. So the statement, the bottom line here is that you do all this very sophisticated analysis in classical general relativity, and it just tells us that this A reduces to W, and the curvature of W is related to the triad via an equation. So we can forget about the motivation, we can just look at this new boundary condition that we have here, and try to see how we can generalize the analysis that John told us in the bulk to include the boundary. Now, classically, what is the phase space of general relativity with this isolated horizon as an inner boundary? Well, the phase space just really consists of A and sigma pairs, because this W is really induced by A, and this 2 form is induced by sigma here. But mathematically, it's convenient to think in this language. That you can say that in the bulk, we have got a phase space which is made up out of A and sigma. A and sigma fills the bulk. And on the surface, there is a phase space which is made just of the U1 connections W up here. In the bulk, A and sigma are canonically conjugate, so the symplectic structure little omega in the bulk, in the volume, is just given by like delta A wedge delta sigma. And on the surface, the statement is that I got this abelian connection, and the symplectic structure here is just given by, if you give me 2 tangent vectors, so W is an abelian connection, you give me 2 tangent vectors to the space of abelian connections, then I have to produce a number, and that number is just k upon 2 pi. And this k is a level that Misha told us this morning, times delta 1 W wedge delta 2 W. This is just the Chern-Simons symplectic structure. And the level k is related, because of all this general relativity boundary condition, to the area. So this really is, classically, the area is huge in the Planck units. Okay? And therefore, the statement is that, well, considering large black holes, so this is a theory with large level, just like Misha was considering this morning. And then the total symplectic structure, if you like, is given by the total Hilbert space. You just pull this back, the volume symplectic structure, you pull back the surface symplectic structure, and the total symplectic structure here is just the sum of these 2 pullbacks. So the total symplectic structure has a volume piece and a surface piece.
Well, you have 2 different R's in your expression for the curvature F. Will you explain those?
2 different?
There's a brown R and there's an R sub I.
It's a gamma. So this is a gamma. This is a parameter. This is just a positive number that John explained. I can tell you later on. This is called the. This is associated with how you formulate your classical theory, which variables you use to formulate the classical theory. Classically, it doesn't matter which gamma you use. They're all equivalent descriptions. But quantum mechanically, the gamma does matter because it gives us. And this R, on the other hand, is just an internal vector. It's just a mapping. I mean, you've got the horizon to sphere, you've got a Lie algebra. Just look at a mapping from the horizon to the unit to sphere in the Lie algebra with winding number 1. That gives you a vector R. That is what. Okay. So the surface phase space, you can think of it as being exactly the U1 Chern-Simons theory phase space. But the two Hilbert space, the 2 states are intertwined by this equation, that the surface curvature is related to some triad operator, if you like, or the 2-form operator in the volume. Okay. So now what I would like to tell you is just heuristics of quantization, and then we'll do the quantization. So heuristically, what we'll like to do is the following. Just as the state space had this nice projection structure, you would expect that the total Hilbert space could be written as the volume Hilbert space tensor product with the surface Hilbert space. This is well understood, and this is what John's lectures were all about, or at least the first 3 lectures were about. And the surface Hilbert space, we know heuristically that it should be related to the Chern-Simons theory. If you have this tensor product structure, then the space of states, which are trace plus operators in this Hilbert space, project down naturally, and we have the same mathematical structure as in the classical theory. The classical phase space is on the last transparency. Now the key condition, this is all heuristic, but the key condition is that F is proportional to this particular operator. F is proportional to this particular field up here. So in quantum theory, the idea is to impose this horizon boundary condition as an operator equation. And when you use it as an operator equation, F operates in the surface Hilbert space, sigma operates in the volume Hilbert space, so you get an equation like that. Now a basis of solutions for such an equation, where I got an identity here and identity here, is just given by states where type one element in the first Hilbert space, tensor product with an element in the second Hilbert space, where psi b is an eigenvalue of this operator with some eigenvector of this operator with some eigenvalue, and psi s is an eigenvector of n hat operator, and the 2 eigenvalues should match. Then I can solve. Then psi b, tensor product psi s, is a solution to this this particular equation. Now, as John told us, that the bulk Hilbert space is completely known, and these are just the triad operators. And so the eigenvectors and eigenvalues of these operators are completely known. What are they? Well, in the bulk, you may have some spin network, and it may be an open network which ends on the horizon. And supposing I got, this is labeled by a spin label J1 and J2, then the eigenvalue of this operator is just given by some constant times. If x is at the puncture, I get something. If x is not at the puncture, I get 0. Therefore, I get a delta distribution eigenvalue. And at ith puncture, the number I get is just a half integer, mi, which is just between minus ji to plus ji. Not very surprising, because roughly speaking, this is a vector operator, and its eigenvalues, if you like, would be really would be j's. But on the other hand, here we are projecting this, so we are computing the r component of the j operator, if you like, and that is why we are getting the eigenvalues again. So this is heuristics, and what it tells us is that we should really think of this f hat operator that we have as being distributional, or its eigenvalue should be distributional on the surface S. And therefore, that means that I should really begin in this quantization by constructing a Hilbert space as follows. I should look at the two-sphere, I should look at punctured two-sphere, where the punctures are obtained by looking at the bulk quantum geometry, or by a spin network in the bulk which intersects the surface at some punctures. So you fix a set of punctures P, and you try to construct the horizon Hilbert space for this fixed set of punctures as the Chern-Simons Hilbert space on that punctured sphere. And then finally, we'll have to add up all the, you'll have to allow various punctures, not just one punctures, but various punctures subject to some condition. So let's just do this now. So this was the idea, and let's just do it. So what is the quantum horizon geometry? So first, we can look at the punctured sphere, and we can construct a surface phase space. So P is a set of punctures. I'm going to construct a surface phase space from Chern-Simons theory. On the surface, on this horizon surface S that I got up here, I'm going to think of, I'm again going to consider generalized connections, exactly the same as the way that John did. Generalized connection assigns to each edge an element of the group U1 up here, such that if I change the orientation, then I should get inverse of the group element. And if I compose two edges, then I should just compose two group elements. So this is the same as in John's talk. Now what we're interested in here is the following. We are interested in the space of all connections, all generalized connections, which are flat except at the points pi. That's what we're interested in. So we got the space of generalized connections which are flat except at those points pi. This requires a careful formulation of what we mean by flat except at these points. Flat everywhere else is obvious, but what kind of singularity do we allow here? But there's a very natural resolution of this. We'll just consider that. And then the statement up here is that of interest to us will be the following. You take this space and you quotient it with a semi-direct product of the U1 gauge group, of U1 gauge transformations which act on the connections, which are all identity at the punctures. So they're arbitrary up here, but at the punctures, they're all on identity. And semi-direct product with the diffeomorphism group on the two sphere. But we consider the identity component of the diffeomorphism group, which of group of orientation preserving diffeomorphisms, which fix each of these punctures, and which we fix a ray at each of these punctures. Those of you who have looked at Chern-Simons theory sort of will immediately realize that this is exactly what one has to do in the quantum Chern-Simons theory, where you have this extra structure in order to get control on this phase space. Once you have done that, the statement is that this is what we would like to call as a phase space of the Chern-Simons theory with these punctures. And then there's a very nice result saying that this space is a very nice structure. This space is in fact diffeomorphism to a 2 times n-1 dimensional torus. And where does this torus come from? Well, not very surprising. I got this bunch of punctures, 1, 2 up to n. I can consider the curvature is all distributional up here. Therefore, these holonomies are all non-trivial. They take values in U1. And these holonomies are also non-trivial. They take values in U1 because they start at a singularity and they end at the singularity. So I just have to specify these holonomies, and the statement is that if I specify these n-1 and these n-1 holonomies, then I have given you a point in this space. In other words, the equivalence class of connections. And so these are just the holonomies. The connection holonomy around gamma i's, which are these loops up here, or these semicircles, and holonomies operating on eta i's, which go around the punches. And then you can work out the symplectic structure. First, you would be worried because you would think that, oh, wait a minute, the symplectic structure may be complicated because the symplectic structure was first defined on smooth connections. Our connections now here have distributional curvature. Is the symplectic structure still well defined? And the nice thing is that yes, it is. Given any two tangent vectors to the equivalence classes of connections, actually the symplectic structure is what it was before, and that just becomes the symplectic structure of the torus. If I take these holonomies and label them by xi's and these by yi's, then I just get delta xi, wedge delta yi. So it's really a torus, and therefore our problem is reduced to quantization on a torus. So, I guess those of you know, this is like the quantum geometry of the horizon is described by a non-commutative torus of dimension 2 times n-1. And so, in order to do this quantization, first of all, what we need to do is to construct a holomorphic line bundle over the phase space with a certain connection whose curvature will be equal to I omega. And then the standard results from geometric quantization tell us that this exists if and only the level is quantized. The level, the Chern-Simons level, takes values as in integers. And this is the same that happens when you do the geometric quantization of angular momentum. So what are quantum states? Well, quantum states are really sections of this holomorphic line bundle, but you can think of them as holomorphic functions on this torus, which you can think of as being, you can think of them as holomorphic functions on torus in some rough sense, and a more precise sense, you can think of them as holomorphic functions on Cn-1, n-1 dimensional complex plane, which is invariant under the discrete subgroup, by which we divided this in order to get our torus. And these are the classical theta functions. So what is beautiful is that all these somewhat abstract ideas from geometric quantizations and theta functions and so on are directly needed to talk about the quantum geometry of a black hole horizon. Now, the Newmanian basis for the surface states is just obtained as follows. You are given a bunch of punches, right? This is what is given to you. Then you can just look at the eigenvectors of the holonomy operators which just surround the puncher. Okay, that's a convenient basis. And the eigenvalues are all of the type 2 pi times bi, where bi's are all integers, which, so all the bi's imply they sum up to 0 mod ck. Okay, here bi's are in integers mod k. So you've got nice eigenvalues here, you've got nice eigenbases here, so I've got an explicit representation of the surface Hilbert space. Now, in terms of SO2 connections, this was all in terms of U1 connections, but I can just go to the SO2 connections. I got a geometry of the horizon, and classically, I can look at a SO2 connection, which is like the Levi-Civita connection, on the surface itself. In terms of that, the statement is that this non-trivial holonomy around these punches just says that there is a deficit angle. And the deficit angle is 4 pi times bi upon the level, and they all add up to 0 of modulo 4 pi. The statement is that you've got this horizon geometry, so if you've got a point on the horizon, then instead of being a smooth surface through that point, there's a little deficit angle. It's really tiny, because as I said, for a solar mass black hole, this number is 10 to the 77, and this is an integer up here, which is not a huge integer typically, and so therefore this number is tiny. I get a tiny deficit angle. For example, bi could be as 1, then I get 10 to the minus 77 times 4 pi as a deficit angle. And this is a quantum analog of the classical fact that the scalar curvature, the Gauss curvature integral is just equal to 4 pi. And this, we get this result because quantum geometry is really probed only to holonomies. Because of that, we always have this mod 4 pi things that are happening here. Sorry?
Why is it modulo 4 pi not atomic exempting 4 pi?
Not 2 pi or?
Why is the sum only 0 pi?
Because in this whole game, we only have holonomies that are given to us. So we really cannot compute sort of deficit. Usually, yeah. So therefore, the deficit angles, I mean, it's not the other way around. Where you can metric, you can compute the deficit angle and then compute the holonomy. Here we only have holonomy that is given to us, and that is not, there is no ambiguity in that.
What happened to the other holonomy?
You can also use the basis in which the other holonomy is diagonalized, which is that this basis is going to be convenient to us. Is that the question?
Well,
Sorry.
you had, this was half of the holonomy, right?
But so it's like looking at P's, P and Q, and you're looking at the P's, but you could also look at the Q's. I mean, that is with other holonomies. I'm going to torus in one direction as opposed to the other direction, just because this is a very direct interpretation in terms of deficit angle. You could also use a basis. They also form a computing set. You can form a basis out of them.
One set determines the other.
In the sense that it's a complete set. So in the sense that it's like I get vectors of two conjugate operators. So and now this is my one diagram of graphs and patterns. And that diagram is representing a quantum black hole. So what does the final picture look like? We're still fixing n punches, okay? I'm trying to describe a black hole with a given area A0. Okay? So how does it look like? Well, first of all, I got all these polymer states. Okay? Classically, the geometry is smooth everywhere. Quantum mechanically, I got this quantum geometry. So we call this polymer geometry or polymer states, or the spin network states coming out in the buck. They go all over the place. They go and puncture the horizon. And at each leg, each edge which punches the horizon is leveled by Ji. And at each puncture, they deposit a quantity of area. And John told us that the area that Ji will deposit is just 8 pi Planck length squared, and the inertia parameter has square root of Ji times Ji plus 1. Therefore, the total area that is deposited by this particular state on the surface is just sum of all of them. Each one gives a little bit of area. But in addition to that, this is the area operator. This is also the triad operator. And the eigenvalue of the triad operator, the R component of the triad operator, is just the same kind of expression, so that there is no gamma up here. And I got here MIs, and these MIs and JIs are related, as I explained a little bit earlier. So these are the volume states. Then we got surface states, which live on this horizon itself. And these, in this particular basis, are given by surface states labeled by integers b mod k, and which are eigenstates of this holonomy operator. Now is a problem that we want to face. We are motivated by this particular heuristic considerations. So we constructed the surface Hilbert space, where the volume Hilbert space, and now we want to know, do they match? Do they give us something interesting together? So what is the quantum boundary condition? As I mentioned before, f is not really a well-defined operator, but e to the f is a well-defined operator. So we have to write down the quantum boundary condition in terms of e to the if and 2 pi gamma upon a0 times sigma. So I just exponentiate this. So if there's an I missing up here, that should have been there. So we just exponentiate the quantum boundary condition, and we want to know, does this have solutions? Now the eigenvalues here are all known. They were just written out up there. Okay? And these were computed using quantum geometry that knew nothing about the Chern-Simons theory. Now I got e to the if hat, but if you think of e to the what this operator is, if I take the field operator and if I smear it around a little disk surrounding the puncture, that will just give me the holonomy operator. That's really the meaning of this operator, value distribution. And the eigenvalues of this holonomy operator are given by e to the 2 pi I times this number b upon k. And we are asking that the eigenvalues of these operators should be the same as the eigenvalues of this operator. This, if you like, has never heard of the volume quantum geometry that John told us about. It only knows about the Chern-Simons theory. I could have given it to Misha and he would have come out and given me these eigenvalues if I told him that the level was k. This operator, on the other hand, has never heard of Chern-Simons theory. So can the two match actually? Do the two sets of eigenvalues agree? And the answer is yes. They do match. You just have to put compare this number with this number and use the definition of the level, and you find that they're exactly the same if you take bi to be equal to minus 2a mod k. So the statement is that they're exactly an isomorphic, and they're exactly the same sets of real numbers that you get in the two cases. And this is not very surprising because there was no a priori reason for this to happen. So we have the bulk quantum geometry, we get the surface quantum states, we have Chern-Simons theory, and we get the classical general relativity isolated horizon boundary conditions. This provided us with the level k up here, and this we used up here in order to calculate this eigenvalue. This also provides the classical general relativity provides us the bulk quantum geometry, and then we got that here. We got this eigenvalue of this operator there, and it's very interesting that the three things to say go in tandem. They match very, very nicely to actually give us this particular complete matching, and therefore the statement is that this picture really makes sense, and the quantum horizon of a black hole can be thought of in those terms. Now, for a black hole horizon, the number of punches is not fixed. Only the area is fixed. So what we have to do is to get all surface states. To get all surface states, we have to change the puncher set. The puncher set, modified one, is given by puncher and a J label. And we allow all such P tilde puncher sets, which have the property that the total area they will give to the black hole is close to A naught minus epsilon, A naught plus epsilon. This is exactly what one always does in forming an ensemble in statistical mechanics. And now, it is this Hilbert space that we have to consider. You consider one set of punchers, you look at the Hilbert space. The dimension of that Hilbert space will be given by product, or I goes from 1 to n, where n is the number of punchers, times 2ji plus 1. Then I go and change my puncher set, such that this is also satisfied. And I'll get another Hilbert space, surface state, and I'll get a bunch of the dimension of that. And I will take all possible surface Hilbert spaces and add up their dimension. The question is, what is the answer? Does it give us black hole entropy? So this is the very last part, and the answer is the following. Before arriving at the black hole entropy, we still have to mod out by the remaining degrees of remaining gauge freedom, because we had to consider gauge transformations, which are identity of the punchers. So there is a remainder u to the n that we have to mod out by. And we also have to mod out by diffeomorphism group divided by this subgroup that we have chosen, which places the punchers, the razor at each puncher. There are several subtleties in doing this, but for the counting, they don't matter. They only say the following. They say the obvious thing. They say that if you want diffeomorphism invariance, it means you should not worry about where the punchers are located. Because if you have got one location of punchers, by diffeomorphism you could map it to any other location of punchers. So what matters is only the number of punchers and not the location of punchers. The final answer is very intuitive and obvious. And then the statement is that we ought to count the number of states that is equal to the dimension of the surface Hilbert space, where surface Hilbert space is a direct sum, the surface Hilbert space together with punchers, where punchers are subject to the condition that they gave us some area. So now you take the log of that, and you obtain the number, and you obtain the area upon 4mp squared, just as Hawking and Bekenstein told us, but we get a numerical coefficient. There's a numerical coefficient gamma 0, which is a pure number log 2 upon root 3 times pi. And there is the immersive parameter. Now the dependence on this immersive parameter is not surprising. Why? Because the quantum of area depends on the choice of the immersive parameter. The value, as John explained, depends on the value of the immersive parameter. So if I take this black hole and divide it up into elementary cells, the minimum area that I can assign depends on the immersive parameter. And therefore the total number of states would also depend on the immersive parameter. So that is by itself not surprising. And we can look at this calculation as fixing the immersive parameter. This ambiguity that we have in the Barbero immersive parameter, we can fix it by looking at black hole thermodynamics. So semi-classical considerations. So if you want agreement with semi-classical considerations, for example, Hawking quantum field theory in closed space-time, then it fixes this quantization ambiguity, this ambiguity that we have in the immersive parameter. Now one might say, well, so you had an ambiguity and you just fixed it. But there are many tests. I can have black holes which are just non-rotating and spherical. I can have black holes with distortion. I can have black holes carrying various charges, like electric charge, magnetic charge, and diatonic charge, etc. I can have black holes carrying spin. And the important question is the immediacy parameter you get? You have only one parameter to play with. You cannot change the value of this parameter as you go from black hole to black hole. If you fix this value, then the theory is fixed. Then you have to go and calculate in that theory what happens if I consider a different kind of black hole. And the answer is that in fact, for all these black holes, independent of black holes, the charges, the distortion, the spin, or you may have a cosmological constant in the theory, the value of this parameter is universal. So there is only one value for which one seems to get a good semi-classical limit. Finally, it is really true that the J equal to 1/2 configurations. So we look at this black hole horizon, and we consider J equal to 1/2 configurations. They will give us the maximum, the minimum area. Right? J equal to 1/2 is the smallest value, so each puncture will have minimum area. That means they will give us maximum number of punctures up here. So if you have got a black hole, it is going to have, for example, for the solar mass black hole, there will be 10 to the 77 punctures. There will be lots and lots of punctures up here, and each of these punctures then will give us, each of these punctures will have two values of m allowed. M is equal to either +1/2 or -1/2, and therefore we will get, so to say, 2 to the n as the number of states, just as John Wheeler had told us. So, in fact, Wheeler's ideas are borne out here in a very precise sense, though. It's not that all states are just correspond to J equal to 1/2. It's not true that everything is just 8 from bit, but what dominates in the entropy calculation is just the states which correspond to Wheeler's 8 from bit. And finally, this is the only entropy calculation that I'm aware of which encompasses these diverse astrophysically interesting black holes, like the distorted ones with arbitrary spin and so on. As well as they also, for those of us or those in the audience who know about cosmological horizons, it also encompasses all the cosmological horizons. There has been always a problem, namely the cosmological horizons also should have entropy, as Hawking and Gibbons argued in the 70s, and the question was how to explain it, and this takes care of everything in sort of say the same framework. And the final thing is the following. The famous calculation of Hawking's in 74, what he really did was to do quantum field theory on a black hole space-time. And what he found was that black holes are not really completely black. Classically they are, but quantum mechanically they are not. Because of quantum tunneling effects, they can actually emit particles. That's what he saw. And as they emit particles, they lose mass. And this loss of mass is realized by shrinking of area. So as a black hole evaporates, so to say, by emitting particles, their area actually decreases slightly. So what one sees here is really, in this picture, that the Hawking radiation is really realized as conversion of quanta of geometry to quanta of radiation or quanta of matter. In the beginning of this century, you see, we learned that radiation and matter are not so distinct. You have all these Feynman diagrams which can convert one into another. First people thought they were distinct. Then Einstein came and told us, well, geometry is also a physical entity. It's not inert. It can be acted on by matter field. Then Hawking, in 74, gave us the Hawking radiation idea, and that somehow brought more close to the idea that something like a black hole, which is a pure geometric object, can actually radiate and create matter quantum. But now we supplement it with quantum geometry, and what we find is that not only this Einstein's vision that geometry is a physical entity is really now elevated to the quantum domain. I mean, it really is a physical entity. You can have quanta of matter, quanta of geometry being converted into quanta of matter. I mean, that's as close to physics as one gets. So I want to stop there. I just want to say one thing, that in both these objects, in both these calculations, the Big Bang and the black holes, the quantum nature of geometry, the detailed framework that was constructed, spin networks and so on, and eigenvalues of geometric operators being discrete, plays a very fundamental role. Thank you.
Thanks very much, Abhay, for a very enthusiastic talk. So we have two things. One, I want to entertain some questions, okay?
second thing is, before everybody leaves, Mr. Lubitsch has something to tell us and announce. So first, let's take some questions.
Yeah.
Can you distinguish between fermionic and bosonic black holes?
No, there is no charge that the black holes carry which will tell you whether it was formed out of fermions or bosons. There is an electric charge that's carried, but that could be either come from fermionic particles or bosonic particles.
This is not really a physical question, but what happens when just before or just after the Big Bang, you have this? Or what does that even mean? If you have a if you have a dissolution of space and time, what does that mean?
It means that we do not have a differential geometry as you know it. Instead, we have quantum geometry. So there is a state of geometry and matter, quantum mechanical state in the Hilbert space. There is a ray in the Hilbert space that describes the state. But we just can't think about that state in terms of classical metrics, smooth things that are given to us everywhere. It is very similar to what the analogy I gave with magnetism, namely that in the paramagnetic phase, there's nothing wrong with the magnet. It's just sitting there, so to say. But it's just that you cannot describe it in terms of a little arrow going from north to south and everything like that. But you have to look at microscopic building blocks, which in that case are spins. Similarly here, we have to look at microscopic building blocks, which if you like are spin networks in matter of quantized. So.
You can still use the words before and after as if there wasn't.
Very good. All right. So the statement is that what one is doing here, and this is the question that John also raised, the issue of time. In this model, which is sufficiently simple, that one can actually resolve this issue of time as follows. One just identifies time, at least near the singularity or some big neighbor of the singularity, with the volume of the universe. So what that equation says is really, when the volume of the universe was so many Planck units, the wave function was so and so. When the volume of the universe is, because it is all expanded in eigenvalues, when the volume of the universe is so many Planck units, you don't have to think of volume as time. But it is very convenient if you want to make some contact with classical theory to think of this volume as time. But the volume is discrete. So in some sense, you really have, if you think of it as time, then you really think in discrete steps.
What you described as a sort of description of black holes suiting to have horizons. Does quantum geometry setup also predict?
No. So the statement is that it's a real problem in almost every sort of background independent framework as to what we even mean by a black hole in full quantum theory. In other words, I give you some state in full quantum theory, and how do we see a horizon sitting in that state? That's a big problem in, I think, in almost every approach to quantum theory. So today, if you just showed me the whole Hilbert space, we can solve the theory and show me the whole Hilbert space. I really don't know. I mean, I don't mean that it's never known. But today, we don't know what will characterize the states which will correspond to the black holes. We did here the opposite way around. We said that we started with the classical black holes, we had a phase space, and we quantized that phase space. And then we get these states, which are this property. Now, this already is giving us hint, in the sense that it is saying that, well, we should look at for such states in the full theory, which correspond to black holes. Now, your question really is that if I look at full quantum theory, then in that quantum theory, I start with some nice initial condition correspond to some star or something, the quantum mechanical formula, and I evolve it. Would it actually form a black hole, or would it not form a black hole at all, which will look like black hole only, at large scales, but not really. There is no real singularity, etc. There is no real horizon. I don't know the answer to that question. Yeah.
Okay, so
It's just one question.
So when Dennis Sullivan came on, would this theory have a semi-classical limit?
Yeah. So what one knows today is the following. What one knows is that this has been a major thrust of work for close to a year now. So there are lots of results, but the thing is that everything is not completely clear, so not everything is published. So let me just tell you what we know. What we know is that in this space, where also the space of solutions of quantum constraints will lie, there are states which will correspond to photons in Minkowski space-time, gravitons in Minkowski space-time. So we know that. We can write down such states up here. We feed in the information that it is really background space-time is Minkowski space-time in the construction of those states. This space is huge, and so it will have states corresponding to Minkowski space-time, some other space-time, and there will be some states which don't correspond to any space-time at all. The thing that we need to do still is really matching. So there are three things that one has to do. The first level, at the level of operators, we started with general relativity, and we, in some suitable sense, we quote-unquote quantize that classical theory. Therefore, if we look at points of brackets, go to commutators, etc., then we'll recover general relativity from, for example, from Thieleman's regularization, because he really did replace points of brackets by commutators. I upon H bar times commutator. The second level is, are there states in the theory which look like Minkowski space, photons, gravitons, etc., etc. And the third thing is, now look at dynamics that was given to us here, and are these states sort of, at least approximately, do they solve the constraint equations, at least approximately? There is a third step which is not done. In other words, we want to tie down the semi-classical states to exact dynamics.
But so do you expect to see the gamma equals gamma naught from that third step?
Right. So there are many checks. Yeah. So there will be many checks which will come, which are needed for the value of gamma naught. It's basically so. We can let me stop right. As far as gamma is equal to gamma naught is concerned, we could really do a calculation now without even carrying the third step. Because I could just take some of the semi-classical state which corresponds to Schwarzschild space-time with gravitons in it, etc., and do a calculation. I'll tell you what calculation it is. It has to do with absorption cross-section by a black hole. We can do a calculation, and that calculation could tell us. So in principle, it can be performed today. Hard calculation has not been done. So we don't have to wait for the last thing in order to get additional support or counter argument